Hello. There you go. Y'all quiet down pretty quickly. Welcome. My name is Charlotte Gilbride, and I'm the coordinator of the Nancy R. Chandler Lecture Series at COCC Foundation. Thank you for being here tonight. I'm going to start off with COCC's land acknowledgement. COCC would like to acknowledge that the beautiful land our campuses reside on are the original homelands of the Wascow and the Warm Springs people. They ceded this land to the U.S. government in the Treaty of 1855. The Paiute people were forcibly moved to the Warm Springs Indian Reservation starting in 1879. It is also important to note that the Klamath Trail ran north through this region to the Great Solalo Falls Trading Ground, and the Klamath tribes claim it as their own. Descendants of these original people are thriving members of our community today. We acknowledge and thank the original stewards of this land. I'm going to try this because I think I was kind of going in and out. Again, welcome. It's so nice to see a full house here at COCC. I'm glad you're here. It's probably obvious, but we are recording tonight's program, so all of you that were registered attendees will be getting an email in the next couple of days with a link to the recorded program. If there's a part you want to watch over, I've seen some of the slides. You might have to do some of the science repeat. I'm kidding. But if you did come in and you're not registered and you would like an email with that link, see me afterwards and I'll grab your email from you. Like always, I want to thank the Nancy Chandler Lecture Series annual sponsors. They are Maybelle Clark McDonald Fund and the Associated Students of COCC. Without these organizations' continued support, we wouldn't be able to do what we do. And what we do is we accomplish our mission of bringing renowned speakers, lecturers, and experts to the region to deliver broad-based programming on a diverse range of educational and topical subjects. And that's why we're all here tonight. So welcome. After Dr. Ray's presentation, we have reserved some time for Q&A from the audience. And both myself and my colleague Brittany will both have microphones, so raise your hand and we'll run around like Phil Donahue and bring you a mic. And that, hopefully we'll get to as many questions as we can. I want to start my introduction for Dr. Rod Ray with something unique and exciting. When I was first talking with Rod about doing this program, he made the decision, instead of taking the normal speaking fee that we pay our speakers, and the normal charge we charge community members to come hear our speakers, he would like to encourage donations to a scholarship fund he founded to honor his mother. That's the Nancy Ray Zal Nursing Scholarship here at COCC Foundation. She was a former faculty member of COCC. Many of you made donations. Yes. Many of you made donations, and thank you. That will definitely impact a student's life whose dream is to become a nurse. And then if there are others who would like to make a donation, we can take those via credit card or check after the program. I have an actual swiper machine. And interestingly, there's more connections with Rod Ray and COCC. He himself attended school here for a year, and his stepfather, Dr. George Zoll, spent his career at COCC. At that time, it was called COC, which is Central Oregon College, and he held the position of Dean of Students and Director of Foundation. So I was kind of amazed that that was one position way back then, right? So Rod and COCC go way back. And now some background on Rod Ray. Rod Ray is the former CEO of Ben Research. Ben Research was founded here in Bend in 1975 as a technology development company. Over the first 20 years, Ben Research provided innovations for separations in the agricultural, electronics, energy, and space industries. Over the next 25 years, Ben Research had an increasing focus on drug delivery technology development for the pharmaceutical industry. In 2014, the company was purchased by a large private equity company and ultimately became part of Lonza, which is a Swiss pharmaceutical technology and manufacturing company. During his career at Ben Research, Dr. Ray held positions starting from research engineer to then advancing to director of engineering, president and chief operating officer, and served as chief executive officer from 2008 to 2014. He was raised in Bend, Oregon, and he attended Bend High School, go Lava Bears, and he holds a bachelor's degree in chemical engineering from Oregon State University, as well as a master's and a doctorate from the University of Colorado. He is a licensed professional engineer in both Oregon and Colorado. In 2014, Dr. Ray founded Canyon Mountain Consulting, from which he currently is a consultant and board member for various pharmaceutical and technology companies. He serves on the board of several nonprofits locally and higher education organizations such as Mosaic Medical and Oregon State University Cascades, where he is also the professor. He teaches thermodynamics and leadership at OSU Cascades. In his free time, he continues to study and research natural phenomena occurring in nature. He is particularly interested in the formation of various patterns found in nature, which is an ongoing pursuit from his graduate studies. So we are in for a treat tonight as he shares with us his latest research. So please join me in welcoming Dr. Rod Ray. You're all hooked up and ready to go?
So thanks everybody for coming. It's really amazing to see people come and actually want to listen to this stuff, and that means a lot to me. I have a couple of disclaimers. The first one is there's a lot of PowerPoint in this, and I didn't have adult supervision on the PowerPoint, so you'll see a few little glitches here and there. I apologize for that. And the other one is I'm told by people I worked with that there's always too much material. So I apologize for that too, but we'll see how we do. And we have questions at the end. Okay, so what we're going to do tonight is talk about patterns in nature. It's really cool, this stuff. And, there's a bunch of them up there. It's hot in here, so we'll try to get to the snow maybe a little sooner than I would have normally. That might help. What I'm going to do is tell you some background, or explain some background kind of on energy and how energy comes in from the sun and goes through our whole environment and goes back out, and how that is what powers weather and patterns and everything. So we're going to do the energy, a little energy background. We'll talk about when patterns form and when they don't a little bit. And I do actually have a math slide in here because I just wanted to have one. You can ignore it, you kind of glaze over, but anyway, it's there. That was for David Bermudez, actually, the math. So. And then throughout this are cell phone pictures, and you're like, really? Why is this guy using cell phone pictures? The reason is, if I took a cell phone picture of one of these phenomena, it means you can too. So my big objective tonight, above all else, is to get you more curious about this sort of thing, and then go out and look for these, and then send them to me. Which happens a lot. So that's what we're after. If I go through too much and all that, it doesn't matter. What matters is that you get interested in these patterns and how they form. So there's one of my cell phone pictures from my mailbox, believe it or not. And then we'll finally, mercifully, we'll get to the actual patterns pretty quick. So, and I have quotes through this. They're all red, so you can, for your amusement. So that's a Galileo quote. So the first thing is, you're probably used to a lot of patterns in nature actually being biological patterns. And what that means, in one sense, that means they had an instruction manual, which is DNA, telling them to be, bees and make honey, or zebras, or tigers or something. That's not what we have tonight. Everything we show tonight is actually just physics. And I don't mean to denigrate physics, but there's no instruction manual. And, so things, when you think about it that way, you see something like a snowflake, it's like, whoa, really? I mean, there's no DNA or anything. So that's what we're doing tonight. And so, clouds, snowflakes, all that. So just remember, no DNA. So now I'm going to talk about energy coming in from the sun. This is good background, but it's also really cool, so that's why I'm doing it. Our energy comes in from the sun all the time, of course. Like right now outside it's pretty hot, actually. And exactly the amount that comes in goes back out. I mean, sometimes it varies a little bit up and down, but generally it's the same amount comes in as goes out. And that's not intuitively obvious because it feels different. So the amount of energy that comes in is 174,000 terawatts, which is, trust me, it's a really big number. And the amount that goes out is 174 terawatts. The cool thing, just put it in perspective, the entire Earth's energy production is 15. So that gives you a feel. That's one of the reasons why people want to do solar energy. There's plenty of energy. So that's cool. The other thing about this is the energy that comes from the sun is really high quality, really useful energy. And, what do I mean by that? Well, it can do a lot of work. Intuitively, you could probably understand this better if you think about the sun as 10,000 degrees Fahrenheit. So the radiation coming off it must be cool. Well, not cool. It must be really great energy. Another thing is you can get a sunburn from the sun. So the energy that comes back off the Earth, remember it's equal to what comes in, that is generated at like 0 degrees Fahrenheit. That's what the Earth looks like from space, is 0 degrees Fahrenheit. And so, again, your intuition tells you that's not as valuable. So what happens to it all? And that's another thing we're talking about. And just to kind of beat a dead horse here, I talked about the high quality energy can do work. So work is things like make weather and evaporate water, which we'll talk about again in a second. And then the lower quality energy is mostly heat. So if you think about, you get a sunburn from the sun and the degraded heat actually just heats you up. So just have this kind of vision that energy in is really high quality and energy going back out is lower quality. So it always finds a way back out somehow. So just a cool way to show you how energy gets back out is, I'm not going to go through hurricanes in detail because we don't have hurricanes here, but I really like hurricanes, so I wanted to have them in there. And this one's named after my son, Ian. And I have a quote here. 2 things Florida can teach the other 49 states: how to make a good margarita and how to deal with the aftermath of a hurricane. That might be kind of mean to Florida people, but... So the cool thing here is, remember, the energy has to find its way back out. And one really neat way it does that is a hurricane. So a hurricane, as you know, happens over, down by the equator, Gulf of Mexico, where it's really warm water and warm air. And that's what drives a hurricane. And again, we're not going to go through all that detail. But what it basically does is it pulls heat off the ocean from the winds, and then that goes up. The air goes up in the outside of the eye and the outside of the storm, and then it goes across the top, which is basically the stratosphere, and dumps the heat off and comes back around. So it's basically a heat engine taking heat from the surface up into space. And the really cool thing is here's a satellite picture of the temperatures, and you can see where it cooled down the ocean as the hurricane moved along. So that's the kind of thing that happens. You don't really think about putting all these together. So next time you're watching a hurricane on the Weather Channel, think about all the heat it's dumping, which I think really cool. So again, what other things does it do? So the energy comes in and degrades. It makes wind. It heats the ocean, like we just talked about. It makes ocean currents. It dumps water up in the mountains, and sometimes as liquid and sometimes as snow, and it melts or whatever and flows down in streams. It comes down in the groundwater. The energy that goes to evaporating the water and makes the rain up high in the mountains is actually stored up by the water being up high, and it can come down and do things like make power. So this is the work that the energy does, which we should be very happy about. The sun heats the earth, the ocean, the lower atmosphere. Warm air rises and does good things. Again, the energy is stored up high and comes out. This sort of thing often looks chaotic and not organized and just clouds and wind and rain. But in fact, shockingly, because we're going to talk about patterns, there's patterns that happen. And so there they are. Okay, so now we're going to do a little science. So we know that there's energy coming in and it's doing things, and sometimes it forms patterns. There's a whole field of science called stability theory, and these patterns are often the result of something called an instability. And I wasn't going to go through this for you, but they're all called instabilities, and I can't help it. So, there's Rayleigh Taylor and Plateau Rayleigh. Anyway, so what is stability theory about? So the ball in the bottom of the little well there, that's stable. If you nudge it, it's going to go back to the same place. That's a stable system. The ball on the top, if you nudge it, we could do a chorus, but it falls off and goes to a different state, and usually a lower energy state. So when one of these patterns happens out in nature, it's almost always an unstable system, like the ball on the top of the mountain there. So this is some of my PowerPoint I wanted to kind of show off here with the arrows and stuff. So again, what we're talking about tonight is primarily unstable systems out in nature, and you can actually predict and do math on this. So another little piece of this is the instability is usually kind of in the form of two forces working against each other, and one of them wins. So that's kind of why they're unstable. Sometimes one's bigger, sometimes another. And again, this is all happening out in nature without instructions. And so again, the perturbations grow. So perturbations, we'll get to that in a second. Perturbations are the disturbances that are always out in the environment and always causing something to nudge, and they grow or they don't grow. And another thing about this, and now you got to brace yourselves because the math slide's coming, but you can predict this, and you can predict when they'll happen. You can predict how big they are. And that's what I did for my graduate work, believe it or not. And it's really a cool field. It's called stability theory, like I said. Okay, so there's the math slide. And, glaze over. But what you do is you write down a whole bunch of equations that describe what's the physical situation. And then you perturb them by putting little variables on them. And then you plug it all back in, and out comes these magic groups, dimensionless groups, these numbers that tell you yes or no. Yes, it's going to form something, or no. So that's all you need to know about all this math. And then there's perturbations around, like a gopher hole in the side of a river, which will make sense to you later, a train going by, a butterfly flapping its wings. And those are little perturbations that either grow or don't grow. So mercifully for you, that's all the background. We're going to get into the patterns, which is actually why you're here. So the first one is called a Kelvin-Helmholtz instability, and we'll get to what reason it's to what it's named after in a little while. That's kind of funny. And that's a Kelvin-Helmholtz instability. Has anyone seen a cloud like this around Central Oregon? Andrew. You will see more now because I clued you in. And so what happens here is you have a stagnant layer or a layer of air that's not moving very fast below, and it's usually more dense as well. So you have a dense air not moving, and over the top of that, you have fast-moving air that's lighter. And the question is, with all that math and all of that, does it form these swirls or these unstable-looking clouds or not? And the answer is sometimes it does and sometimes it doesn't. And sometimes the conditions are right to see it in clouds. I was going to talk about where the energy came from. The energy, of course, in this case comes from wind. So remember all the energy cascading through. It's wind and heat. So here's our physical situation. My professor taught me to always do the physical situation. So what you have is lower density fast-moving air, higher density not so fast-moving air, and if the conditions are right, the energy in the top layer is enough to dig out pieces of the bottom layer and swirl it up. And that's the way to think about it. And those will either grow or they'll fade off, like we talked about with the little ball things on the mountains. And, there's some math, but when you do all that math, usually you get a number always named after some person, which we'll talk about later. I've never understood all that. But, the number is the force balance I talked about. In this case, it's buoyancy, or how light or heavy the air is, versus how much that air is moving, and the balance. And if, the number's above a certain amount, then it goes or it doesn't go. And that's going to be the case in all of these. So this is a little movie. I was taught never to do this in one of these presentations because it never works. But that's one forming in a laboratory, and also never do it twice. But watch that. The top layer is slipping down, and the bottom layer is slipping down, and the top layer is being pushed back, and they go off when the shear gets to be enough. Isn't that cool? It's really cool. These guys are very clever guys that made this experiment. And so here it is close up, and then we'll move on. But watch it. It goes right. It gets to that number, 0.25, and it goes. So that's cool, right? So this is the picture I took from my mailbox. So I literally nerd out walking around Central Oregon, and I got to get a better phone. My daughter has a better phone now with a good camera. But there's some there. There were some tonight when we were sitting at lunch over the hospital. We could see some. This is, you've seen this, right? This is what they look like from underneath. And this is a little more common because you're usually underneath, not to the side. And then this was, one morning I was actually sitting at my desk in this really boring phone call. Your board meetings are way better, Patty. And I'm looking out and I'm seeing, wow, look at that. Those are, okay, and you got to stretch a little on this, but there they are. And it was a cold morning. The air was stagnant over the airport. And and it was zipping by up above, and you could see stuff going by, clouds, and it formed these little, it was trying to do it. And then another thing is, if you think about it for a minute, the ocean's heavy and a fluid, and wind goes over the top of it, so that's our situation, right? But there's the ocean is hard to move. It's harder to move than the air is, and that's intuitively obvious too. So it has to get up to a certain place for it to happen, and that's about 12 knots. And so when you're at the ocean or a lake or something, pay attention to it, and you'll notice that waves actually don't come until it's 12 or 13 knots. They're just ripples before that. And it can be terrifying if you're in your sailboat, which we are there. So 20 to 35 knots, you got lots of wind. And then here's a cool thing, is you can tell stuff about Saturn, because you guys now know all about this. You're experts, right? So if you see this picture, in a publication or a paper or something, there they are between the rings of Saturn. So what's that tell you about the rings? They're slipping past each other. Well, that's information we may not have known without something like this, and that's really cool. And then my daughter, who's sitting right over there, is a helicopter nurse, and she likes this stuff, and she sends me pictures all the time when she's on the job. There's one now. There's my daughter. You'll recognize her. She's right there. So anyway, you got to embarrass your kids. And then there they are over Seattle. And my quote, which I just found in a bathroom recently. And these people maybe don't look like so much fun. And there's a bunch of these people that aren't from these parts that look like this, and you wouldn't want to go out with. And they named this stuff after themselves, which is just amazing to me, but it's not cultural. We'll get to more of this later. So now we're on to our next instability. This is called Rayleigh-Taylor instability. And we'll start this with, did you know there's palm trees in Ireland? I didn't. And there they are. I mean, it's really, those are palm trees. Why is that? And even more so, there's Europe, and there's the United States overlaid on Europe, and so Ireland is way north of the entire United States. So it's up way north of Vancouver Island. It should be cold, right? It's not cold. It's warm. I've been there. You sit outside at the bars. So what's going on? Well, what's going on is this thing called the Atlantic Meridional Overturning Circulation, which, all you got to remember is AMOC, or if you don't want, just call it the Gulf Stream. That's close enough. And the Gulf Stream's the red part down below. And what the bottom line here is the Gulf Stream goes on shore in Ireland, and that's why it's warm. That's actually why Europe is habitable, is the Gulf. So the Gulf Stream's actually pretty important if you have real estate in Europe. And Ireland's winters are actually 10 degrees Fahrenheit warmer than they should be, which is a cool thing. And that's due to the AMOC. So what's the situation here? And this is kind of cool. So in this case, you have heavy liquid over light liquid. Now, doesn't that feel unstable to you? Okay, now think about this. We're moving on a little in the science here. If it's unstable and the heavy's going to go down and light's going to go up, is it going to do it in a great big thing like that? Like that? Or is it going to do something else? And it turns out it does something else. It does that. And this is where the math and physics all come in. It's lower energy to do this than it is to do that. So the math will predict this. And you get the current. And our force balance here is buoyancy over how thick it is and how hard it is to move, viscosity. And our energy comes from the heating of the atmosphere. So what happens if you do this experiment, you get growing fingers that go down, and again, you can predict them, and it happens pretty fast, just like that movie did of the other one. And it's always unstable. This one doesn't have a threshold. It's always unstable. It sometimes takes a while, but it's unstable. So, and this one's blurry, and this is why I made the PowerPoint comment. So what happens here? What's going on? Up north, it's here. Old people fumble around for things. Up in the north, it gets cold, and the salt water gets cold, and it's heavier than the warm salt water down below, so it sinks. So the salt water sinks down, up here where the ice and all of that is, long nights. It sinks down, and if it sinks down, some water's got to replace it, and that turns out to be warm water that comes up from the Gulf. And it's oversimplified, but that's how this whole thing works. So you might suspect what's going to happen here. And that's what makes the red one is all that warm water coming up, and the blue one is the cold water going back down underneath. Okay? So now we have this little problem. And I don't want to start any controversy, but in fact, the Greenland ice cap is in fact melting. There it is from space. And there's a lot of fresh water out in the ocean because of that. And fresh water is lighter than salt water. So it's even more. So it starts to kill this Rayleigh-Taylor instability. The density starts to go close to the same, and so they don't go. So now you have fresh water, lower density, and it starts to slow this down. And it turns out it has been slowing down for a long time, but it's accelerating now. And there's natural cycles of this, but there's an accelerating cycle. And the blue line is the amount of water that's come off Greenland since about 1900 or so is where it started to take off. And this other line is the strength of that AMOC current. So it was already changing a while back, but in fact it's accelerating. And this is a bad thing, because like Ireland last winter had -10 centigrade temperatures and unprecedented cold, and it killed a bunch of our palm trees. So this is something to really worry about, and you can now, when you read about this, you know a little more about it. And there's our quote, which isn't really funny, but there it is. And then there's one more manifestation of this instability. There's the wine glass thing, there's the ocean currents, the Gulf Stream and so on, and there's volcanic eruptions. So that is a mushroom cloud. It's not from the other thing, it's from a volcano. And what's happening here is light, hot air is being blasted out of the volcano, and it has some stuff in it so you can see it. And it goes up because it's lower density and it has some momentum. And it goes up until it hits air that's the same density. And then it doesn't want to go up anymore, so it spreads out. And that's how a mushroom cloud works. And that's a Rayleigh-Taylor instability. It's this particular thing, a volcano one, is called a pyrocumulus cloud. And it's a huge release of heat, and I already explained how it works. This one is from a thunderstorm in Siberia. And the sad part of this is the people that lived in Siberia thought someone had dropped a bomb on them. And that actually happened. It was a big thing, and it turned out it was a thunderstorm. And now you know why but it's amazing it looks like that. And then this is one I took about 2 weeks ago. Now, we could have a little argument. This might be a stretch, but I had to have a cell phone picture, and I saw something that at least looked like a mushroom cloud, so there it is. And I don't know how to make little red boxes. I only know how to make big red boxes, so sorry about that, too. And here's our guys. Here's Rayleigh again and Taylor, and it's clearly a certain kind of guy, right? So. Okay, now into another one called Plateau Rayleigh instabilities. This is a little more tricky, and we'll see how this goes for me explaining it. But how many people have seen this? Everybody, right? It's really cool. It looks good in the sun. But when you think about it, how come it's not just a cylinder of water? But when the water condensed on there, how come it just doesn't stay a little cylinder? And the answer is it's unstable. And it's all about surface tension. So I got to tell you about surface tension quickly. Pretty cool, huh? If you have water, let's say like a drop like this, the molecules down in the water molecules attract each other. They want to be together. And down in the middle of this, they're pulled in all directions, and they just all kind of go like this. But if you're a water molecule up on the surface, there's nothing pulling on you up here except air, and that isn't nearly as attractive. So these molecules they kind of act like rubber, actually. They try to pull to get together. So they're pulled inward, they're minimizing surface area, and so instead of a sheet of water, you get a drop. Because they want to have the lowest surface area per volume you can have. So that other one's really cool. I really like that picture. So that's cool too. And the reason that's happening is, the same thing. This happens to be flat. It's like in a bowl or something. But the rubberness kind of thing of the surface, it'll hold up a paperclip or water skipper. And that's really. Now, if you took a corner of soap and touched it on the surface, it would lower the surface tension, and the little paperclip would, go down. So you've seen this on your sink, where there's just a little column of water coming out, and it breaks, if it's the right volume, the flow rate, it breaks into droplets. The same reason we just went through. In this case, what happens is one curvature from the perturbation. So train goes by, little perturbation on the surface. Those are trying to pull each other together and be a drop. But the ones that are on top, they're going the other direction. So sometimes this is unstable, sometimes it's not. And you can do the math on that. And there's kind of another way to look at it. If it takes off and wants to form drops, you actually get flow in that little cylinder, away from the dips, and that's how it breaks off into a drop. So there you have the droplet, and then if there's too many numbers here, but in fact the important thing is for water, the surface tension is like 70 in those units, and the viscosity is like 1 in those units. But for honey, the surface tension is a little lower, and the viscosity is a lot higher, and so it's much harder to move it around. So if you do the same experiment, it doesn't form drops. And the math predicts that, and that's really cool. So this is the cell phone picture. This is at Rainbow Chair one morning at Bachelor, and as you know, that chair is really slow, so you have to just kind of have something to do, and I took this picture. And so this is one that did everything we just talked about, but it was really cold, and then it froze, but in those wavelengths of the droplets. So isn't that cool? So this is the kind of thing I want to get in like the email or the mail from you, is this kind of stuff. Okay. And, you're sensing it, but here comes your quote. And this is the controversial one in the talk here. But it's not mine, it's Larry's. That's the whole reason I'm giving this talk, actually, is to show this quote. Okay, and here's our guys. Rayleigh again and Plateau. And there they all are. And I've already made my point. In the modern world, this wouldn't happen, right? Anyway, so they're fun guys. Not all of them named it after themselves, but some of them did, which is inexcusable. Okay, now we're going to do snow, and that's good because, it's too hot and all that. So snow is super interesting in a whole bunch of ways. I have something to show you in a little while that I made up that Andrew and I had to see if Andrew thought it was right, Andrew Ketzover here. So we'll show you that. But snow it does the same thing hurricanes does. It takes heat out of the earth, and I'll show you that. But it makes these crystals, which we're all amazed by all the time, and they're always six-sided. So we'll talk about that. So what happens is you have supersaturated water in the clouds up there, really high, and it's colder up there than freezing. But it doesn't freeze for a while until it gets dust or ice crystals or something. So you have water up there, and you have water molecules, and water molecules actually really like each other. And so if it starts to condense, the water molecules all jump together, and we'll go through that, and ultimately make this crystal. So what's going on? And this is this little bit of a story here. So again, you got the water molecules in the air. There's what they kind of look like, and water molecules are really polar, really special molecules, and there's kind of only one way they can fit together as a group, and when they get together, they very quickly form this crystal lattice, which actually Einstein worked on, and Linus Pauling from OSU worked on. And this has a particular structure. It starts to be a hexagon right at the beginning, because that's how the molecules want to be. And then it grows. So sometimes a molecule will come in and it'll hit on one of the sides and stick, and sometimes it'll hit over on one of the little, where there's a little peak, and it jockeys for position, and it's sometimes easier to go flat on the flat part and sometimes easier to go on the point part. And ultimately you end up with that hexagon up there. So now you have a six-sided hexagon. Doesn't look like one of those snowflakes yet, but it looks like that. And this is maybe half a millimeter, let's say, in size. When it gets to that size, another thing happens. So what happens is it gets bigger and bigger, and these branches start to form. And the short story here is here, which is it's a longer, once those little protrusions start, it's a longer ways from the bulk of the water vapor to get to a flat place than it is to get to a peak. And that's called diffusion limited. And once it's diffusion limited, these little peaks grow a little bit more fast bad English, anyway, faster, and then they grow even faster because they're even closer to the water, and so on. And that's what happens. So that's how you get the little tendrils. So you've got one thing that happens in the first half where it's kind of reaction limited and tries to be the shape that it originally was, and it just grows. And then at the back half of the snowflake formation, you get these little peaks because it can't get enough water to all parts of the hexagon. It can only get it to the peaks. So that's how snowflake works, in short. And there they are. Now there's another thing. your intuition might not tell you. Snowflakes, or a snowstorm actually takes, it's oversimplified, but it takes heat from the Earth and the lower atmosphere and pumps it out into space. And the way it does that is snow is made up in those clouds, remember, over the Tetons there, and it falls down, and it comes down to where we are, and at some point it's warmer down here, the atmosphere of the Earth, and it melts the snow. And what melts the snow? That takes heat, right? Like melting ice. That comes from the Earth, and so it's putting heat into the water. The water goes back up. It doesn't actually do it in this nice little path like this, but it sort of does. I mean, generally speaking, it goes back up. And up at the top up there, it freezes, and it has to dump that heat back off that it used to melt in the first place. And that heat goes off up high and goes out in the atmosphere. So isn't that cool? A snowstorm is pumping heat from the water, from the Earth up into this atmosphere. Now, I made this one up, so you should be a little suspicious, and I did check it with Andrew, and he had a couple of, he generally thought it was okay, though. So I think that's pretty cool. So I also give this talk to third grade, fourth graders sometimes. This is my granddaughter's class, and we make a snowflake out of the kids. So we first make a hexagon, and then we make the dendrites. And it is actually hard to get the kids into the flat parts, and they want to be on the peak, and it all works out. And so anyway, see how they're very well organized, and it worked out. There's our quote. Okay. And now the last one I'm going to explain in detail is, some detail, is meandering rivers. This is actually my favorite one because it took me a long time to figure this one out. And the way I'm going to explain it may not quite satisfy you, so you got to go read a little more. But it's really interesting how this happens. So I'm sure you've seen meandering rivers, and I'm sure you've wondered how they could be so regular, because it's just an obvious question, right? But some of these are just exactly the same distance apart. And how does that happen from a straight river? That's not intuitive, right? So remember that all that energy is degrading, and as it degrades, it's pumping water up high, and you're getting potential energy in the water that's up high, either in snow or lakes or whatever, and it flows down and makes a river. But it starts out straight usually, and they've done experiments of this too. The first river was straight, and so why does it form these? So you ask yourself, why does it do this? And how do they form, and why are they so consistent in wavelength? And it's, guess what, an instability. It's a very subtle one, but it's an instability. So it's the little ball on top. So the river that's straight is the little ball on top, and the river that's meandered is the little ball on the bottom down there where it's stable. So it stabilizes itself, is what it does. So that's cool. So at a critical number, a critical set of conditions, it will not be straight, and it'll follow a perturbation and start winding, and at a certain wavelength. And you can predict that mathematically. It's very tricky, but you can actually do it. Very clever guys figured this one out. And I read this stuff for like 2 years before I believed it. So what's going on here? And this is complicated, but what's happening, it's sort of like energy flow again. You have energy in the water up high, and it's flowing down, and it's in a straight river. So the problem is it doesn't like being straight. It doesn't like going as fast as it's going. And also, there's a rough bottom. There's rocks and pebbles and stuff on the bottom. And the water's going over the top of that, driven by its energy, and it starts to churn up, or it does churn up, induced turbulence, puts energy up into the water. And that bottom one is the bottom of the river churning along, and goes up. The energy goes up in the river. The other one is a top-down view. The thing about this that's really, really subtle is when you put that energy in the river and the flow is right. If the flow is right and everything, it will start to form regular eddies. So the whole thing's flowing, but the water's also eddying. And then you get a disturbance, which this happens to be a gopher hole, which I thought was kind of cool. This is really in a paper, actually. and so if there's a little disturbance, if this is enough flow and there's enough energy around, it'll take off. And once it takes off one place, it takes off everywhere. And the guys have done this with sand in the lab, and it really does do this, which I just find fascinating. So once it gets going, it's cutting on one end, on the outer edge, and dumping material on the other. That's what people study, but what they don't really always understand is that's not really what's interesting. What's interesting is how it forms in the first place and what the wavelength is. So you can model this. It's a function of depth and width of the river and the velocity of the stream, which is not shocking. And the one on the left is a picture of a stream on my ranch. It's the cell phone picture. There's another picture from the daughter of a couple of meandering rivers. I think it's like Klamath Falls kind of area-ish. Yeah. So they're all over the place. They're up in the Ochocos everywhere up there, if you notice. And another helicopter picture, there's another one there taken off. Mostly I just want to show pictures of my daughter flying around the helicopter. But you figured that out. This is up in Yellowstone. This is the Gallatin River at the very upper end of it in the snow. Cell phone picture. And there's our quote. Okay. So now, happily for you, I'm just going to run through some and not explain them necessarily because, for one thing, they don't know why they form. So I think maybe you've seen these out in the desert if you drive to John Day or Ontario down the Malheur. There's these stripes out there. And in my opinion, no one knows why these form. There's these papers around that say it's because golfers made ditches, but how did the golfers know to do it like in this wavelength, right? Are they unstable or what? So I don't buy it. And there's these things called beach cusps, which there's work been done on this. I talked to one of the world experts at OSU, and he suspects there's more to it, but I don't think they know. But that's something like the meandering rivers. There's some kind of circulation that goes on. And then there's avalanches. I'll show you more about this in a minute. So first off, everybody's seen, these are basalt columns, and this happens to be in Yellowstone with my cell phone. And there's what they look like from the top. So what's going on there? Why do they form these hexagons? And man, we've seen a lot of hexagons today, haven't we? So nature likes hexagons. So what's going on here, and this isn't very satisfying, and I said I wouldn't explain it, but basically as lava cools, or as anything dries out or cools, it shrinks. And if it's shrinking, it's eventually got to crack once it gets to where it's shrunk so much that the strength of the material makes it crack. And it turns out, if you go through all the theory and the math and everything, the lowest, or the way that's most efficient for it to crack and dump all the energy of stress and strain is a hexagon. And that's not very satisfying, I know, but that's really what's going on. There's a lot more to it, like whether it's water cooling it or air, but that's what you're seeing. There's a blurry one that I took from Warm Springs. So just think about it as the lava comes flooding out and then cools and forms a crack up where it cools, and it propagates down and makes these columns. And then you buy one of these and make a fountain in your yard. And the same thing happens on lake beds. It's the same deal. The mud is not so strong, and it shrinks, and it wants to crack. Those aren't perfect hexagons, but you get the idea. Again, it doesn't have DNA, right? And this is the one that really amazes me, is I just found this like a few days ago. There's a hexagon in the pole, up at the polar region of Saturn, that no one really knows why it's there, but it's there, which is amazing, right? What's that doing? And look how regular it is. It does have something to do with the kind of wind they have on Saturn and the patterns of that, and that all comes together. But I got to figure that one out too, if somebody has. And then the final one of these, this is the one I worked on in my master's degree. This is called Pattern Ground. That's a blurry image from Sweden, but it's a hexagon, and you find this up in high mountains. They're up in the Cascades, So what's going on there? And what's going on there is it melts down in the summer and you have water over ice, and the water is actually at 4 degrees is heavier than it is at 0 degrees, so that 4-degree water wants to come down like light, and the light water wants to go up like we've talked about, and that makes little cells. And that melts the ice in these patterns. And then when it refreezes, you had rocks grow in your garden after winter. You have to go out and get rid of the rocks. It does that and pushes them in these directions and makes these patterns, which I know is kind of fast, but that's what's going on. At least I think so. And I spent a summer up in the mountains digging these things up and measuring the width and the depth, and my math had predicted the width to depth ratio, and that's the data. And there's people that there's a controversy in the literature, which is actually really cool about this. And I asked this guy in Washington if I could come up and talk to him about it, and they never even answered me. It's just so controversial. It's really fun. I even said Dr. Ray, and I'd never do that, but it didn't work. And then there's the beach cusp I talked about earlier. You know, the funny thing about this is this will happen on a beach one time of the year and not another time of the year. And when you notice this is on the Oregon coast, if you're walking along the beach and you find yourself doing this, if you looked at it from the air. So now you know enough, you've seen enough of this in an hour, you know there's something going on along the lines of what I've talked about all day, right? It's just, I don't think they know exactly why yet. And then there's avalanches. Are there any civil engineers in here, by any chance? Let's do that. Because I really like to tease them about why would you build a road below these avalanche paths? And the answer is always because there was nowhere else to build it. Really. That's not how we do chemical engineering, honestly. But anyway, these are evenly spaced. This isn't great, but you can see there's a spacing to this, and you can kind of feel it. And I'm always looking for this stuff. So we're in a bar in Joseph, Oregon, up by the Wallowas, and I look up and I see that. And they're those are almost exactly the same width. So what's going on there? And it has to do with snow up high and finding the best way down and the strength of the snow. No one, to my knowledge, has worked on this. There's some theory around sand dunes that's applicable, but no one's really worked on it. And then there's one where Mary lives in Bozeman. That's the Bridgers from the airport cell phone picture. And there's some more of our stripes. So what's going on there? And this is cool because I managed to get a meandering river, the stripes, and some basalt columns in the same cell phone picture. Pretty good. So Charlotte moves, so I must almost be out of time. So that's the physics and the patterns, really cool. And I couldn't help myself but do, one of these. Okay, if this talk works and people look interested, let's push it a little further. Okay, so this is about leadership and a little bit about life. And stick with me. Maybe this will be something we talk about outside. But I look at companies in this circle where they're usually operating over here, number 3. Let me back up. So there's a company, and it's sitting there, and I'm modeling it here. And there's the outside world that needs stuff. They need drug technologies, or they need, donuts or something. And the company recognizes that there's a need, and they do work, and they make value. So customers can buy it, shareholders get money. So that's going on all the time. Oops. So usually you're operating over on the left side where you're just trying to make your business run better. It's just churning along, you're optimizing things. But if you're the CEO, and I learned this the hard way, you have to be suspicious that all is not well. And we better be looking for changes in that outside world. And so you look for patterns, shockingly. And so, you get the metaphor. And when you see a pattern, now we know that there's an underlying reason for the pattern. So if you're looking out at the world and you see some kind of pattern, then you got to go figure out what that's about and find the future state of your organization to take advantage of that pattern and understand the why, like we have done all day. And then you have to make that happen. You got to go through change and then get it all optimized again and go through the cycle again. But it's all about the patterns. So that's what the leader does. What's the root cause? What's our desired future state, which is the vision? You hear the word vision. That's what it means. What's the future state of the company? The plan forward, that's the strategic plan. And value added, like I said earlier. And I got 2 examples for you, and then I'm done, except for all these questions you're going to ask. So a couple of examples of patterns. One of them is we realized, well, there's a whole new generation of drugs out there. When Charlotte mentioned we shifted from a whole bunch of NASA and separations and things over to pharmaceuticals. Why did we do that? We had a customer that told us the pattern is that drugs are becoming more specific and they have properties that make them harder to deliver. Randy back there did this with me, wherever Randy is. There he is. And they needed new technology to deliver the drugs. For example, a lot of these drugs are very, very hydrophobic. They don't like water. And guess what you're made of? So you put one of those drugs in you without technology, it just kind of goes through and doesn't do any good. So we recognized that pattern. And we went on with a partner to develop new technology against that pattern. And our vision became to be the preferred company for science-based advancement of new medicines. So that was about the technology. And it worked. And this is a long story there, but Bend research worked. I mean, it did really well. This worked. And then there's one, I was doing consulting for the fire department here in Bend. And by the way, vote for the levy. So the pattern, the fire chief and I were talking, the pattern is there's a lot of distrust in various government institutions, and he's aware of that. So we were talking about visions and things. So what's the opportunity? And the opportunity is to focus the organization on serving the community and building trust, which is the way these guys are. And so they have this kind of draft vision, which is to be unquestionably trusted. And that's their response in the public sector to the lack of trust. And who better but the fire department? So there's a couple patterns for you. And we have a couple quotes. This is in the Quran, that you can't live without a vision. And I'm done. Happily for you. And I actually do have one more slide to put up while we're doing questions. It's my favorite. Well, that's a quote from Carl Sagan. And I was thinking today, if you haven't read Cosmos, even though it's really old, read Cosmos. It's a really cool book. And then that's my all-time favorite quote, which to me says, learn from your mistakes and don't take yourself too seriously. Okay.
Thank you. Thank you. That was amazing. Now,
you think an engineer would figure out whether.
I know, but we threw this microphone on you at the last minute, so you had one less hand. Now, Rod would like to take questions from the audience. And I don't know how many questions there'll be, but just out of respect for time, try to keep your question to a question rather than a real long-winded comment. How about that? So just raise your hand, and I'll get to you and speak for Oygen's camera. Please speak clearly into the microphone so those on the recorded audience can hear the question.
Regarding snowflakes.
Yes.
You always hear there's never two alike. Is that true or not?
I knew that question was going to happen. It's a really, really great question. What that means is I didn't pull the wool over your eyes with the example of how that forms in the first place, so that's great. The snowflake shape has to do with the exact environment around the snowflake as those things are happening, as it forms the hexagon and as it starts to form the dendrites. And if it's a little bit different temperature or a little bit different water concentration, it will form different. And so every one of them is different. But they're the same all the way around because the environment isn't different over that far. And you can do it in the lab, actually, but out in the world, they're all the same, but they're all different. And that's because their environment is a little bit different. Great question.
Yeah.
Thank you. Regarding the graphic with the stability and instability, it seems to me like the ball on the top when it rolls down, that there's a big release of energy. Does that energy get harnessed in any way?
Good question. Yes. I mean, yeah. Here, the system's sitting there and it's full of energy, let's say because it's up high in the mountains or water vapor that hasn't condensed yet or something like that. But it's unstable. It's at the top of that peak. And it really wants to not be that way. It wants to be stable. It wants to be a crystal snowflake or a meandering river. And so that is a release of energy. The condensation / crystallization of the snowflake takes energy to do. The meandering river has to cut those banks, and that's why it doesn't want to be straight. It has too much energy to have a fragile bank. It wants to have a bank that's such that the energy of the river is stable. So, yes, I mean, it goes from unstable to stable, and there's a release of energy that, in the case we went through, forms a pattern. Not always, though. Still releases energy, but not as a pattern. Great question.
So I'm still trying to formulate the question in my head, but it relates to, we're talking about visual patterns, right? And so are there patterns that aren't visual necessarily? So the clouds, for example, that have this beautiful look to it, does that have a certain sound to it that's a pattern? Is it all visual?
I'm sure. Let's see. Think of an example. But yeah, I mean, if it happens fast. But you know, a river, like if you walk along a river that has meandered, it's going to be noisy where it's cutting the bank and placid where it's dumping the soil. But I'm cheating a little because that's already happened. Snow doesn't really make any noise when it's doing its thing, I don't think. So I have to think about that, but it makes sense. I mean, the energy can release any old way. Yeah.
Here you go, sir.
Any systems actually keep sleeping? Can you feel a natural system just doesn't work?
That don't do this?
Yeah.
Well, the granite one, you know, if it won't erode, it won't work. But if the physics is such that if you have all the information and you understand it, like some of these, and then it's going to do it. But if it doesn't do it, you don't understand something, and you need to learn more, and that's the lesson. So it's a good question. This is a very philosophical science group.
Anybody around here? Okay. Here you go. Mm-hmm.
Do you think the increasing number of storms and the increasing intensity is an effort of the planet to maintain homeostasis?
Yes. I mean, there's more energy. I mean, the amount of energy coming in and out is actually still always, it's the same. But more hangs around. I mean, it's warmer here. It doesn't mean there's not the same energy going out. For a little while, it's built up a little bit, but mostly it's just the same going through. But the warmer it is, the more stuff happens. So, yeah, I mean, that Greenland thing, it doesn't matter your opinion about climate change, it's melting. So, but it did that before, too. And it's true that happened thousands of years ago as well. But yeah, it responds, always. I mean, if it can. There's a really cool thing where some guys did some very cool work on the meandering rivers where it's water channels on melting glaciers. And they looked at the meanders that formed there, and that was a heat transfer thing instead of an eroding thing. And they came to the same conclusions. So there you have a different system doing the same thing, completely different system. One's dirt and one's ice.
Hold one sec. I need to be that.
So if it's always heat out and heat in, so there's this balance. Why are we kind of all whacked out right now where everything's getting warmer, and how's that happening? It's not
Right. So that's, I had the number, I did the calculations on that because I knew I'd get the question and I left it in the car. But for a little while, I mean, there's more greenhouse gas, so our atmosphere is acting like a greenhouse a little bit more than it used to. It's not that much actually, but it's a little bit more. A little bit more CO2 and a little bit more methane and a lot more water vapor, which is actually the biggest greenhouse gas, or the most effective one. But if you look at the numbers, it's like 1/100% of the energy in sticks around, or is stuck around for a while and warms us up and goes back out. So it's not quite right to say it's exactly as much comes in as goes out, but it's really, really close. So the part of it that has warmed our atmosphere, that energy is such a small fraction you wouldn't think it would have any effect. But in fact, it actually really does. Because you're doing the average over the whole Earth and there's a lot of energy. So it's one of these things where I didn't quite say the right thing. It's not quite the same, but it's really, really close to us. It's like 1,000th or 10,000th. And I had the calculations and everything, but yeah, and that little bit makes big, we're finding that out. And that's happened before when we had like a lot of volcanic eruptions, thousands of years ago, the same thing happened. Or not the same, but something like it.
Your turn.
So is the phenomenon of equal in, equal out unique to Earth because of our atmosphere? Because we share the sun with all these other planets and we see the same thing on Saturn. So is there a way to know that?
So we have a rocket scientist right here. What do you think, Andrew?
Here, let me give you the mic. You want the mic?
Yeah, I wasn't prepared to be part of the conversation.
You must have
Thank you,
known.
Ryan. I appreciate it. Yeah, when you talk about energy in equals energy out, that just means that you have a constant temperature system. And so the temperature of some of those other planets are going to be very different, but they're still constant. So it's still the same effect of energy in equals energy out.
Yeah. So
Look at you, unprepared and all. You have a question?
Yeah.
Okay.
Is the terawatt input per day or per year?
that terawatt number is constant. It's what's happening at that exact time. If you want to know how much happens over a day, you have to do like terawatt hours or terawatt days. And you know, it's cool you asked that question, because that's where juniors in engineering get screwed up all the time. So pay attention to your own question and learn about that, and you'll be out ahead of everybody. Does that make sense? So one of them is kind of gathered in, and the other one's constant.
Yes.
Good question. Really good question. Which is not unexpected from that family.
Any others? We have just a few more minutes. Okay.
Thanks, Ron. Curious about the disruption of the Gulf Stream. As that changes, are there any patterns emerging you're observing?
Well, first off, that's not my field, so I need to make that disclaimer. But the big one is the Gulf of Mexico, which is where it originates, is so much warmer than it's ever been, that the models that they have for, let's say, hurricanes in the Gulf are kind of not working very well. So that's a change for sure. And then you have, as it goes by the East Coast, and it's changed actually pretty significantly, and that changes sort of the wave action and sort of what it's like on shore in the southern United States quite a bit, and up north it's making it quite a bit colder. So there's a lot of change and patterns there. But personally, the one I'm terrified about is how much warmer it is down in the southern, down the Gulf of Mexico and so on. And the models that we have, you know, you see the European model and the whatever model, those are informed by data from hurricanes that have happened. And when you get the warmest Gulf you've had in recent memory, the models aren't informed in that part of the temperature spectrum. And so we've seen some hurricanes spin up down there. The Weather Channel guys are going, what's going on? And that's because it's just happening. There's a bunch of nonlinear build on itself stuff that's going on. So there's that pattern. And it really worries me about a big hurricane hitting somewhere like Miami, where at least in New Orleans they had pumps. So I don't know if I answered, but there's a lot going on there. The northern Atlantic is not always colder, it's actually warmer in some spots because the whole circulation has changed because of the temperature difference. Because there's less water going down south in the first place. So yeah, and I think that's going to happen in a lot of things with different temperatures.
Okay, time for one more, if there is any. David Bermudez at the Benton Science Station.
So this actually is a question and a response to the question about sounds. And so the surface of the sun, the granulation that you see on it, where it sort of looks like a pot of boiling water, it seems hexagonal to me on a certain level and looks a little bit like the patterns you were showing up in the mountains with the rocks and the cooling. And so have you looked at those patterns before? And then my next question was, I know that they kind of made audio sounds of it, and they didn't know that it was making sounds, but that movement of plasma seems to actually make sounds, which ties in with the question before about whether there's sounds in these things that we see but don't necessarily hear.
Great answer on the sound stuff. The sun part, I don't work on that, but it's really fascinating, and it's definitely cyclical. And we get more northern lights 2 or 3 days ago. We haven't seen in a year. That cycles in the radio interference, all that. So that's really cool stuff to study. I just don't do it, but all the same stuff happens. That kind of stuff. The sound thing's really interesting. I'll give you one example. I was thinking about today, a contrail from a jet, which we see a lot here. If you look along the edge, you'll see Kelvin Helmholtz going on there. Almost every time. And that's probably got sound with it, I bet.
All right. Y'all had some great questions.
David let me off easy. It could have been a lot worse.
Okay, David, you have a harder one, don't you? Yes, so we're all tasked with emailing or texting Rod pictures of things we see around Central Oregon in our travels. How about that?
Perfect.
Yeah. All right, well, thank you all for coming.